Hello everyone, today I'll present ConQuest, queue analysis in the data plane. I'm Xiaoqi Chen from Princeton University, and this is a collaboration between us and Techneo and AT&T. Today's talk is about something everyone hates, which is long queues. When we are waiting at the airport, we are frustrated when there are so many people in front of us lining up. When we open our phone and want to call an Uber ride, we also are frustrated when we have to wait for 25 minutes before anyone will show up. Well, there's no physical queue in this case, but there's a virtual queue. So many passengers, not enough drivers. While I was watching a soccer game live streaming on YouTube, I'm also frustrated when I see the video start to rebuffer. Well, this is also queues. It's long queues inside the network. Let's give a quick recap on how queuing works inside our networks. A network router will have several different ingress ports and several egress ports. When a packet comes in from the ingress port, we first do some routing decision on the packet to select one of the egress ports. And then there's a crossbar that brings the packet to the corresponding port. And then there are the queues before the egress port. For today's talk, let's focus on one queue and one egress port. We also assume the queue was first in, first out, or FIFO. And for more other cases, we discuss in the paper. Let's say when packets show up on the ingress, we first do the routing decision. And unfortunately, these two packets all go to the same egress port, so they have to be queued one after each other. And then they will go out the egress port one by one. Queuing here is necessary for us when we do packet switching to achieve statistical multiplexing. However, once we have a queue, we may have very long queues. Maybe there will be a lot of packets show up simultaneously, all going to the same egress port. In this case, the queue will start to fill up. Now the queue is full. The next packet cannot enter the queue. It have to be dropped. Well, this packet may carry the data for our favorite soccer game, so the video starts to rebuffer, and the people watching the soccer game are frustrated. Or even before the packet starts to get dropped, long queues already cause high delays. A higher delay will impact interactive applications, such as gaming, so the player of online games will be frustrated. So we know long queues will cause delay and jitter that's bad for interactive applications. In particular, there's a phenomenon called microburst. If we plot the queue length over the course of the day, we will see that the queue is really short in most of the cases, but sometimes the queue becomes really long, and then it goes back to normal immediately. The duration was under a millisecond, but within this millisecond, we have high delays and high jitter. We call this phenomenon microburst. We already know that microbursts exist in data center networks, and one of the reasons is called incast, where one server sends many requests to many different other servers and get too many replies simultaneously. Knowing the reason, we can fix it. We can adjust the application running those servers to avoid incast. However, microbursts also exist in carrier networks, and we still do not fully understand their root cause. In fact, the very figure we've shown here comes from a carrier network router. Moreover, in a carrier network, we cannot adjust the behavior of the host, so we cannot use the host to monitor or mitigate a microburst. Traditional network routers provide us very limited visibility into what's happening in the queue. They only give us cross-grain statistics. For example, the switches we used to plot this figure only give us one data point per second. So we don't really know what's happening in the microburst, and by the time we see it, the harm is already done. The user watching the video or playing the game is already unhappy. Luckily, today we have the P4-enabled programmable switches. We can use them to produce real-time, fine-grained queue analysis. So now it's possible for us to answer which particular flow is causing the queuing. We want to answer this question: why am I waiting? Or more particular, which flows has many packets in the queue while I, as a packet, waited in the queue? Let's show an example. First of all, when a packet arrives at the queue, we can look at its content to figure out which network flow it belongs to. For example, by looking at source IP and destination IP pairs. Let's say this packet belongs to flow A. Now, more and more packets comes in, they belong to flow B, C, and D, etc. Now, this white packet may wonder, why am I waiting in such a long queue? I'm suffering from a high queuing delay, so who's causing this delay? A clever Smurf may show up and say, hey, I know, this is because of flow B. In particular, flow B occupies almost half of the queuing space, so this is contributing to the high queuing delay experienced by this white packet. This is just like when someone was waiting for Uber and wonder, why am I waiting for so long? The Smurf may show up and say, hey, it's because there's NBA game just ended in town. So yeah, a lot of people are calling Uber, so you have to wait. Knowing the reason, we could do better. I'm not saying that don't fly into San Francisco immediately after an NBA game, but maybe we can do something about flow B. We could deprioritize it, reroute it, or maybe drop some packets to make sure we don't have such a high delay. Today, we present ConQuest, which answers the question, why am I waiting in a long queue? To answer this question, we can first try to think about a strawman solution. Why not just maintain the flow size in the queue table to remember how many packets for each flow are in the queue? So for example, when a packet from flow A shows up, we'll just maintain a counter and increment it to 1 to say there's 1 packet from flow A. When more packet comes in, we just maintain more counters for different flows. Now, the problem is we have to subtract a counter when a packet exits. So here, when packet A getting out of the queue, we subtract a count to 0. This requires us to access memory when we update the table, which means we have to make memory access when packet getting out of the queue. Then, for more packet coming in, we have to increment the count as well. So we have to make another memory access while packet are entering the queue. This causes conflict here, so we can't really achieve it. The reason was we have to process so many packets per second. In a 100 Gbps network, we have to process 1 packet every 6.7 nanoseconds. Therefore, for the high throughput, high-speed programmable switches, they don't allow us to do concurrent memory access, because otherwise, there's 2 different points we have to access memory every 6.7 nanoseconds. It's very hard to implement concurrent memory access, as we have to prevent memory hazard. Therefore, the architecture of the programmable switch doesn't allow us to do this. We can only access memory either before or after the queuing, but not the same counter from both ends of the queue. The memory is partitioned before and after the queuing. Our solution for this problem is to use snapshots. We slice traffic into smaller time windows, and each snapshot will record t equal to 4 packets in this example. Let's say we have some packet coming into the queue. We do not access memory, we do nothing when packet coming in. Now let's say when packet A getting out of the queue. We made 1 memory access to use snapshot number 1 to record this packet. Now the green packet is gone. Another packet from flow B exits the queue. We'll also add it to snapshot number 1. Now let's say another packet comes in, we'll just add it to snapshot number 1, and so on and so forth. Now snapshot number 1 is full. We'll actually start to work on snapshot number 2. Now let's say there's a burst of packet coming in, we'll just write it to snapshot number 2, 3, 4, etc. This particular white packet, just like before, suffered a very high queuing delay. So by the time it exits the queue, we wonder what happened. Well, we first add it to the current snapshot, which is S4. Based on the queuing metadata, we know this packet enqueued at an earlier timestamp and it dequeued at the current timestamp. With a high delay, we may want to ask, why am I waiting? To answer this question, we have to look at these packets that already departed from the queue. We don't really know it, and they're gone. Instead, we can look at a few recent snapshots. By looking at snapshot 2 and snapshot 3, we kind of captured what are these packets. By looking at these 2 snapshots, we recovered an approximate count for the size of the flow inside the queue while packet E was waiting. By looking at these approximate count numbers, we can figure out, yeah, flow B was a majority of the packet there, so flow B was probably causing trouble. So maybe we can take some action to immediately suppress flow B from keeping bursting to the flow and contributing queuing delays. We use different snapshots to record time window T. Every packet coming out of the queue, we write it to 1 snapshot. We also read a few past snapshots to figure out the size of different flows. However, there's a problem. We only have very limited memory size in the data plane. The good news is we only need to read the constant number of snapshots. We can divide the maximum possible queuing delay by the time window to figure out the maximum possible number of snapshots to read. However, we need to clean the snapshots in order to reuse them. We cannot use the control plane to help us as the snapshots are being rotated really quickly. The time window T could be smaller than 1 millisecond in this case. So we cannot let the control plane to synchronize with the data plane and perform the cleaning all the time. It will be too busy for the control plane to struggle between different snapshots. Instead, we have to clean that within the data plane. Our solution is to use round-robin snapshots to perform clean and reuse the snapshots directly within the data plane. Let's show the example as follows. Let's say right now we're writing to snapshot number 3, which is clean. When a new packet arrives, we add it to snapshot number 3. We also write some zeros into the data structure of snapshot number 4, in this case, to try to clean a little bit of it. Now more packets come into snapshot number 3, and we'll write more zeros to snapshot number 4. So by the time snapshot number 3 was fully written and we have to move on, snapshot 4 is already cleared. The Smurf is really happy because without any outside help, snapshot has become empty. So we just rotate the row of these snapshots and start to write to snapshot number 4. This finished one time window. To recap, today we present the ConQuest data structure. We slice traffic into smaller time windows. For each packet dequeue from the queue, we write a packet into the latest snapshot. We also read a few recent snapshots to figure out what's happening in the queue. Finally, we also clean the oldest snapshots such that in the next time window, it's already clean, prepared to be written. In this way, ConQuest allows us to analyze the size of flows inside the queue in real time whenever the queue becomes long enough. Now let's present some evaluation for ConQuest. The first question in our evaluation is ConQuest accurate enough? We use a Python-based simulator of the ConQuest data structure to simulate the effect for changing data structure size and other configurations. We use the University of Wisconsin IMC10 paper's data center trace to simulate a network, as this is one of the only public trace we can find that exhibits a huge burstiness. The goal for ConQuest is to try to find flows occupying more than alpha fraction of the queue. Alpha is a configurable parameter. We use precision and recall as the metric for identifying the large flows in the queue during congestion. Precision here means if we identify a flow, it's large, we didn't identify any small flows as mistakes. And recall here means we identify all the flow that's occupying more than alpha fraction. Here we present the results. For different alpha fraction here, ConQuest consistently achieved over 90% of precision and recall, which means it's really accurate to identify which particular flow was occupying a large fraction of the queue. However, can we actually improve network performance? We built a testbed with P4-enabled barefoot to Fino switch using a prototype P4 program with 4 snapshots. We built a bottleneck scenario where we have a 10 Gbps link being filled quickly. There's a sender server sending 1 million TCP flows into the receiver side. And then the sender also occasionally sends some synthetic bursty flows to try to cause queuing on the bottleneck link. We tested our idea using a flow-based ECN. ECN here means early congestion notification, which will trigger a TCP congestion control mechanism. Here, if we find out the queue is long and one particular flow is causing others to wait, which means one particular flow is occupying a large fraction of the queue, we will add ECN flag to the flows packets to make sure it's throttled. And we compare that with a baseline where whenever the queue length exceeds the threshold, we'll add ECN tag to all the packets. Here we show that flow-based ECN reduced the flow completion time of our workload. The x-axis was the size of the bursty flow, and the y-axis was the flow completion time. As we can see, when the bursty flow gets larger and larger, the flow completion time gradually increases. However, if we enable flow-based ECN, we can reduce the workload flow completion time by as much as 11%. If we look deeper at the queue length over the course of a burst, we can see that in the baseline case, the queue goes longer and longer up to a threshold and then start to oscillate around the threshold. If we enable flow-based ECN, then this particular bursty flow is immediately throttled, and then the queue length remains short over the course of the entire burst, which means other flows also experience shorter latency. But then there's a very huge problem here. Not all the network devices support P4, so they cannot run ConQuest. There are hundreds of thousands of devices into this carrier network, and then there's queuing issues everywhere we need to debug. We can't replace all of these switches overnight with programmable switch. However, we need to analyze queuing in those devices immediately. We need queuing analysis right now. We present a novel setup to use a tapping link and a P4 switch to analyze queuing on any legacy network device. Here, we tap the ingress and egress link of the legacy device to see a mirrored traffic. When the packet coming into the legacy switch, we see a copy of the packet sent to the P4 switch, and we record the timestamp here. When we see the packet coming out of the legacy device again, we'll see another copy, and we'll record the timestamp when this particular packet getting out of the queue. So now we have two timestamps for the packet in queue and DQ. We'll use this data and run the same ConQuest in the P4 switch to analyze queuing in the legacy device. Here, let's show some result about when we analyze legacy device. In this figure, we show two lines. The red line shows the particular delay measured by the P4 switch. Here, almost every packet gets matched and assigned a particular queuing delay. And the blue dots here actually represents the queue length reported by the legacy device. Recall that we only get one sample per second. Instead, we get almost one sample per packet from the P4 switch. These two results perfectly align, which means we are accurately tracking the queuing delay. Our results show that we can still achieve over 90% of precision and recall when trying to find the bursty flows causing the delay in the legacy device. Using this setup, we have successfully deployed ConQuest in two different real-world networks. In the Princeton University, we have been using ConQuest in the P4 campus initiative to debug queuing issues in legacy devices. In AT&T Labs, we have been using ConQuest to analyze the production carrier network's queuing and burst characteristics. In summary, today we present ConQuest, a round-robin snapshot data structure running in the data plane of high-speed programmable switches. ConQuest can identify individual flows contributing to microbursts in real time. By throttling these bursty flows without affecting other flows, we can improve the workflow flow completion time by as much as 11%. So, now the Smurfs waiting in long queues can finally answer, why am I waiting? Thank you.